Chapter 2 of Biodemography is on life tables. In this first module of the chapter, Module 2.1, I will cover the life table basics and other material shown here in red in the table of contents. Life tables are important tools because they provide an organizational framework for mortality data. They provide detailed and transparent descriptions of the actuarial properties of a cohort. They generate simple summary statistics that are useful for comparisons, such as life expectancy and cohort survival. They can disaggregate mortality data by cause of death. They provide information useful in mortality forecasting. And lastly, they serve as models of stationary, that is, zero population growth. There are two types of life tables. One is the cohort life table, which provides a longitudinal perspective from the moment of birth through consecutive ages until the death of all individuals in the original cohort. There's period life tables, which are cross-sectional. They assume a hypothetical, that is a synthetic cohort, that is subject throughout its lifetime to the age-specific mortality rates prevailing for the actual population over a specified period. The basic life table is what's called a single decrement life table. All forms of death are lumped. It's complete, that is, all age classes are included, and it's a cohort, that is, longitudinal data. The radix of a life table is a number arbitrarily made the fundamental number of a system of numbers. In human demography, a typical radix is assigned a number such as 100,000. However, the radix is often assigned the value of unity, that is 1.0, so that subsequent survivors are expressed as the fraction of the original number. The life table radix is the single most important number in the life table because A, all numbers can be traced to it, and B, it initializes the organizational stage for the life table. The most basic and widely used life table function is cohort survival, LX, which is defined as the proportion of a newborn cohort surviving from birth, that is x equals 0, to age x. Cohort survival, designated the LX, is computed using the formula LX equals NX, that is the number alive at age x, divided by N naught, which is the starting number, where N naught and NX denote the number of individuals alive at age x, at age 0, and age x respectively. The second life table parameter, denoted PX, is age-specific or period survival probability, defined as the probability of surviving from age x to x plus 1. It is computed from the LX schedule as PX equals LX plus 1 divided by LX. Whereas LX denotes the probability of a newborn surviving to age x, PX denotes the probability of an individual that is alive at age x surviving to age x plus 1, in other words, the next age interval. The complement of period survival is the age-specific or period mortality, denoted QX, and defined as the probability of an individual dying in the interval x to x plus 1. This parameter is computed using the formula QX equal the difference of LX and LX plus 1, all divided by LX. This can be re-expressed as 1 minus the ratio of LX plus 1 and LX, which in turn equals 1 minus PX. So the sum of PX and QX must equal unity. The fourth life table parameter, denoted DX, is the fraction of the cohort that dies in the interval x to x plus 1. This parameter is computed with the formula dx equal the difference between Lx and Lx plus 1. This parameter represents the incremental decrease in Lx due to mortality within the age interval. The last parameter is age-specific expectation of life, denoted EX. It's defined as the number of years or days remaining for the average individual age X. The value of EX is computed as the sum of life years, or life days, remaining to a cohort age X, normalized by the fraction alive at age X. This computation can be demonstrated using the number of life years remaining to a newborn, that is, expectation of life at 0, determined using the LX schedule as E0 equals the average of L0 and L1 plus the average of L1 and L2 through the average of the next to oldest and the oldest age. The fractions in the right-hand expression give the midpoint values for survival between Lx and Lx plus 1. These midpoints represent the height of an imaginary rectangle centered at this midpoint. Given that the area of a rectangle is the product of its height and width, where the width is 1, that is 1 year or 1 day, the midpoint value thus equals the area. In other words, the midpoint value equals the number of life years lived between x and x plus 1. It then follows that the sum of the midpoint values for all of these imaginary rectangles under the Lx curve gives the remaining number of life years or life days beyond age x, i.e. the life expectancy. The computational formula for Ex is derived by bringing the denominator for all of the fractions outside the expression and summing the duplicate Lx's. Thus, EO equals 1/2 the sum of the expression inside the parentheses. With the exception of L0, there are 2 of every Lx values due to the computation of averages in which each value is used twice. Since the value of L0 equals 1, then the product of this and 0.5 is in fact 0.5. The coefficients equaling 2 fall out, so the expectation of life at age 0 can be computed using the shorthand formula given here. The general formula for expectation of life at age x, Ex, is given as this expression. The inverse of Lx normalizes the accumulated life days beyond age x. Note that the summation index always starts at x plus 1 and not at x. This completes Module 2.1. In the next module, I will cover life table construction, where I get into the nitty-gritty details of life table parameter computations.